Now we have come to another very important topic, which is Gauss law. So remember, there are two Gauss law. This is the first Gauss law. This is Gauss law in electrostatics. Next one in magnetism. So this is first Gauss law, and again this is your most important question. So please mark it this as most important. So till now I have told you that there are two very important questions. First one was that dipole in electric field, and now the second most important question from this chapter is the Gauss law with its application. So these are two most important questions. Almost every year you get a question from these two most important questions. So please mark it as very important. So let us go. So what we are doing in this is we take a sphere. This is a sphere, not a circle, but a sphere, and we take a volume, this surface area element delta S. So again this is a solid angle, a cone. Since this is a sphere, so this is a cone, and there is a charge small q inside this sphere. There is a sphere, charge q is inside this sphere at the center of this charge q, and we take a very small area element delta S on its surface. Okay, so now the radius of this surface is small r, and this area element is delta S. Now let us first understand this one thing, then we will move further. So this area element delta S, this is on the surface of this, and radius. So similar to previously, the direction of this area element is outwards, because we always take outwards, not inwards, and the direction of this radius element is also in this direction. So the cos theta is cos 0, that means 1. So the direction of the radius element as well as the direction of this surface element, both are in same direction, hence cos theta is cos 0 and their magnitude comes as 1. So this we will just use. So that's why I clarified it to you right now. So remember, we discussed about flux. Flux was simply delta phi, which was E dot delta S. Now if we define this electric field, that is 1 upon 4 pi epsilon naught, charge q and the distance r square, the distance between this point and this element, what is that? That is r, because for whole sphere the distance will remain r, and this unit vector r and this area element s. Since this unit vector r and this s are pointing in the same direction, so we simply take it delta s. Why? Because unit vector is only direction, and when both the direction are same, so magnitude remains only because of this delta s. So we reach to this point where delta phi is simply charge q. This is 1 upon 4 pi epsilon naught, this distance r square, and this r, unit vector r dot delta s. Since both are in the same direction, this has a magnitude of 1, this has a magnitude of delta s, and direction is cos 0 1, so into delta s. So simply the multiplication is delta s. So that we got here, So ultimately what is the flux? Q upon 4 pi epsilon naught r square into delta s. Since the magnitude of unit vector is 1, that's what I told you, the magnitude of this unit vector is 1. So again, if you see this r dot delta s, if both are in same direction, so the cos theta is cos 0, so this will come as r delta s, and this is 1, so leave it. So this is simply delta s, no, not vector, only magnitude. Okay, so now let us move further. So let us take, if this is only a very small area, if this is a very small area delta s, then we need the flux through whole sphere. this is a small area, so if we need flux through whole surface area of this sphere, so what we will do, we will make small spheres on this surface of this sphere, small surface on this whole surface, and then add them up. How? Let us say if we have a rectangle, so we can take small rectangles, and with the help of these small rectangles we cover this bigger rectangle. Similarly, there was a sphere and we are using small surfaces to cover the whole surface area of that sphere. So now this is total flux is sum over all surfaces. This is remains same, q upon 4 pi epsilon naught r square and delta s. So now we are summing up it over all surfaces, all delta s. Since each area element of the sphere at the same distance r, so again the r remains same for whole surface. So if this is a sphere, so r will remain same whether you are here or you are here, because it is a sphere. So total flux is q upon 4 pi epsilon naught all delta s into delta s, and this becomes the whole surface area. So the radius remains same, that's why we took it common, took it outside this. This q is constant, 1 upon 4 pi epsilon naught is constant. Why did we take r outside this? Because for a sphere r remains constant, so this is out of this summation, and in the next time summation of all delta s is s. So this is the equation. Now as total surface area for a sphere is, you know, it is 4 pi r square. Simply we put into this q upon 4 pi epsilon naught upon r square into 4 pi r square. So 4 pi and 4 pi cancels out, r square also cancel out, so this is remaining q upon epsilon naught. So this is remaining q upon epsilon naught, which is a general formula. So what is remaining? Total flux is q upon epsilon naught. So remember, this is a very general formula, q upon epsilon naught. Equation 1.30, that means this is phi is equal to q upon epsilon naught. Equation 1.30 is simple illustration of a general result of electrostatics, which is called Gauss law. We state Gauss law without proofs. Here we are stating this Gauss law without proof. So what is this Gauss law? Gauss law says the total electric flux through a closed surface S is always q upon epsilon naught, where q is the total charge enclosed by a surface S. So what does this mean? Suppose there is a charge, this is the charge q, okay, and there is a surface. This is a random surface. In the second case, let us say we take a sphere. In third case, let us take this thing is a simple cube. Let us take this to be a cube. So what does this Gauss law say? Gauss law says this thing is a cube, this is a sphere, and this is a random surface. So what does this Gauss law says? It does not matter what is the surface. It does not matter what is the surface and surface area. So here it is a cube, here it is a sphere, here it is a random surface. So the flux out of any closed surface, so you know that if there is a charge, it will emit electric field out of this. So because of that, there would be a flux. That means electric field lines going out of unit area per unit time. So flux out of any shape will always be that charge divided by this permittivity of free space. That is Gauss law. It does not depend on the shape of the surface. See here, the surface area S is gone. It is simply q upon epsilon naught. So the flux will always be the charge enclosed by the surface divided by the permittivity of free space. Phi is always equal to q upon epsilon naught.